For example number 5, it's a two-part question. And what we're going to do is we're going to use the idea that if a function is differentiable, then it is also continuous. So to show continuity, if we show differentiability, then we also show continuity. Okay. So here's what we're going to do. We've got some function, call it f of x, and that is equal to 3x squared over x to the third minus 2. So we could show that this is continuous using our definition of continuity, or we could just show that f prime, we need to show this is continuous at x not equals, what do they say, 1. Okay, so what we're going to do is we're going to evaluate the derivative at 1. And evaluating the derivative at 1, if it exists, then it's continuous at 1. So watch. Let's just get f prime of x. Well, to differentiate this, take the low times the derivative of the high minus the high times the derivative of the low over the low squared. So now, if we plug in 1, the question is this defined? Can we calculate f prime at 1? And the answer is yes, because the denominator is not 0 when we plug in 1. When we plug in 1, we'll get some number in the top. It's really irrelevant what we get. But in the denominator, I'm going to get 1 cubed, which is 1, minus 2, negative 1, squared, positive 1. So I have a number over 1. So this is just whatever the numerator is. The key point here is that we differentiated and we checked it at that value. And since we found the derivative, we can compute it at that value, then that means that it's continuous. Now where is it always continuous? Well, it's continuous wherever this guy is not 0. So x to the third minus 2 squared whenever it's not 0. Well, that's x to the third minus 2 times x to the third minus 2. Okay, we don't want it to be equal to 0, which means that x to the third minus 2 can't be equal to 0 in either of these cases. So if I go ahead and I solve that, that gives me x to the third should not be equal to 2, which implies that x should not be equal to the third root of 2. And so, as long as we don't take the third root of 2, as long as we don't look for continuity at the third root of 2, it'll be continuous everywhere else. Okay, let's go ahead and try another one here. So for b, we need to show that f of x being equal to the square root of x squared plus 2x plus 1 is continuous at x equals 0. Now, it's funny because they switched from x naught to x, so we can use x naught as well here. I think they were trying not to confuse you. Okay, it's irrelevant. So what we'll do is we'll go ahead and we'll take a look at the derivative of this. Now, as soon as you see the square root, you're thinking, I wonder if it is continuous at that value at 0, because it's not defined for the negative. Now, it could be right continuous or left continuous, but the original square root function is normally not continuous at 0. So what about the square root of this guy inside? Well, let's check this guy out. So let's take f prime of x. So I'm going to do a substitution here. I'm going to let u be equal to x squared plus 2x plus 1. So this is the square. I need to put my d dx in there. So d dx of the square root of x. And we can't, square root of u, because we let u be equal to that. Now, I'll use my chain rule here. So this is du dx times d du of the square root of u. So du dx is 2x plus 2, And then d du is just 1 over 2 square roots of u, which means that f prime is equal to 2x plus 2 over 2 times the square root of u, which is x squared plus 2x plus 1. Now, if we plug in 0 here, on the numerator I get 2. On the denominator, I get 2, which is equal to 1. So 0 doesn't cause a problem here. If I plug in 0, I still have a valid f prime. Okay, I can still evaluate it. So since the derivative exists at 0, it must also be continuous at 0.